Awesome. Good morning, everybody. Thank you very much for coming. I was really not sure how many people were going to show up, especially after how great the party was last night. At least I thought. 9:30 comes very quickly. But I really appreciate everyone showing up, and hopefully you're ready to dig deep into the bowels of performance of the web platform in either Windows Store apps as well as websites. So my name is Jonathan Carter. I'm a program manager on the Visual Studio team, the team that builds both the diagnostic tooling for Windows Store apps written with JavaScript in Visual Studio, or if you're building web apps or websites in IE11, we also develop the tools in F12. And so as the name of the talk implies, really what this talk is about is if you want to build web apps, either targeting the Windows platform or the web platform, and you want those apps to be very well performant, and you want them to feel fluid, and you want them to feel snappy, and you want them to feel fast, what is the tooling experience like that helps you to achieve that in a way that's a bit easier than would be without them? Okay, so the quick agenda of this talk will be mostly demos, but essentially I want to do a few things. One, I'll do a kind of obligatory discussion on why performance is important, because I do talk to a lot of folks that don't necessarily appreciate the value of that. And then once we kind of set that context, I want to then talk about a set of scenarios, performance scenarios that we're going to cover in this talk that are very critical. I'll touch on a few others that are covered in other talks, but primarily we want to figure out what are the types of performance scenarios that we're going to be able to address with the tooling I'll talk about. And then I want to just go into a lot of demos to show how we can address performance issues with JavaScript-based apps. Okay, so why is performance important? A lot of times I speak with companies and developers, and they don't necessarily think of performance as a feature. It's more of a consequence. Either your app, you write it, and it performs well, or it doesn't. And you hope that it does, but maybe it doesn't, right, for one reason or another. And it could be very arcane. But in reality, when looking across trends and historical evidence of apps that were successful, there is a high correlation with the performance, the reliability, the stability of the app, and its perceived value to users. Right, so here, this chart that I'm quickly showing was a report done by Business News Daily that just helps kind of make that point clear that a lot of times in app stores, whether it's iOS Store, the Windows App Store, Android Store, when an app is receiving low ratings, there's a good chance that it's due to performance problems. Right? Either crashes, which could be out-of-memory issues, or low frame rate, or just responsiveness problems that you're trying to interact with the app and it doesn't feel snappy at all. Right? And so in general, if that holds true, then no matter how nice your UX is, and no matter how rich your feature set is, it could still fall flat if your performance wasn't very, very good. Right? And so in addition, I had a couple of snippets from apps in the Windows Store that I thought were also very exemplary of this, where essentially this review is someone on an anonymous app that I'm not going to mention, but is basically saying, hey, the game is good, I like the game, but it's just too laggy. And so that's preventing me from being able to enjoy it, right? And that's a shame, because it probably was a great story and the graphics were awesome. And then here's another one, right, where it says the refresh rate is just so bad it makes me feel dizzy, right? So in both of these cases, there's just an issue with the fluidity of the animations, and just the interaction with the app is just not very good. And so really, we do recognize that it's an unfortunate consequence in some cases that we have to think of performance as a feature, right? It cannot be something that we just address as we have to down the road. You really have to think about it up front. Now, the last two slides that I just showed were kind of more on the App Store side. And a lot of times when I talk with people about that, they say, well, that's fine if you're building apps for devices where there's actually an app store and you're accountable to people because they can review you poorly. But if it's just a website, well, then I can get away with the sins of my performance because nobody's going to complain anywhere anyway. And that might be true. It's probably there. I'm sure there will be a Yelp for websites at some point. But either way, there is also lots and lots of evidence that shows that a website, in order to be successful financially, also has to care about performance, right? Things like page load, like the basic fundamental concept of just requesting a URL and having it complete or finish loading. If that is too slow, that could be enough friction for someone to go to a competitive website, right? And that's unfortunate, but it's the case. It's the truth. And the thing that's even more kind of critical about having to care about performance is the fact that many of these studies have shown that, as that quote mentions, even as little as 250 milliseconds of time can be enough to create a perceived lag or problem in an app's performance. And that's kind of even an abstract concept. Like a quarter of a second just doesn't even seem like something people could perceive, but unfortunately they can, right? And so that just kind of drives home the point that when we think about performance, it can't be just the blatantly obvious 10-second loading process or something that's just blatantly egregious. You really do have to care and think about how can you fine-tune your apps as much as possible. Okay. So summary kind of that is that two things kind of are the crux of why performance is becoming more and more important. One is that the expectations of consumers are getting higher and higher, right? Games running on tablet devices are as rich in some cases as games running on platforms. And so you really have to have a very rich performant experience because the bar has been set so high, right? And then in addition, because the device ecosystem is growing so rapidly, you have to make sure that your app or site, right? So in the case of a website, which has the benefit of having a broad reach, you want to be able to accommodate low-end hardware or any hardware for that matter that a potential customer could access your site. And so you cannot only optimize for a powerful quad-core desktop machine, right? Okay, so that's why is performance important. Hopefully some of that seemed to resonate, right? Performance is still hard, right? So this talk is definitely not meant to say it's easy and it's important, so just go do it, right? Because as I'll show, hopefully the tooling that we've provided will lower the barrier, but there's still a complexity to doing performance analysis. Okay, so that said, once we know that it's important, what are some things that we might want to care about? Some scenarios or some patterns that we might want to look for? So one that's probably very obvious to you all is page load time, right? As I mentioned earlier, it's especially critical for websites. It always has been, really. And it's just the same as important for web apps as well. And so a few additional supporting quotes here just kind of make that point of, there really is a financial tie and user retention to load time. And so really, you should want as a goal for the first screen of your app to be painted as quickly as possible, right? And anything that isn't contributing to the generation of that first screen should not be spending any CPU time, any network resources, anything. And so that's really that scenario, really thinking about what are the resources that you're loading and how do you optimize those. So then in addition, you have this notion of UI responsiveness, input lag, just the general snappiness of the app, right? So once the page is loaded and the user starts to interact with it, does that feel responsive? Does it feel like they're interacting with it in a way that's natural? Does it feel almost real, right? The funny thing about software is that we're all trying to essentially emulate reality by making animations seem so fluid that they seem like it's actually moving, or making form elements or UI paradigms that seem so real that it's natural for a user to interact with it, right? And in the real world, you wouldn't expect to pick up something and there'd be a lag where it's I mean, if that happened, then I would probably go to the doctor, right? And so if you have that in an app and a user goes to scroll or to click a button or do anything and there's that jitter, that stutter, that's just going to be intuitively perceived as a problem. Like, people will see that as a problem. And so you really don't want any of that, right? And essentially, the brother of UI responsiveness is just fluid animations. So these are scenarios where you're not necessarily interacting with the app, so there's not a problem or the need for it to be able to respond, but it's that you're trying to create the illusion of motion by having some animation, right? So in games, this is very critical, but even in apps, more and more. You look at the Windows Store UX paradigms, and it's very heavily lends itself to having subtle animations that have things smooth in, smooth out. And those little effects really do go a long way. And if they're not fluid, a user will catch it, right? And then finally, one that I think is the least most cared about is the notion of long-term stability or reliability, right? So the first three are things that you can notice pretty blatantly, right? A user is going to see that, oh man, this page is slow. Or I can't play this game because every time I click the mouse, it takes a second to respond. But the notion of long-term reliability is that if you want to have an app that has the notion or the user scenario of running for a long period of time, then you want to make sure that that app actually can sustain itself over a long period of time. And that has many factors to it. That has battery, right? You don't want your app to be draining the battery on a device that's on battery so poorly that it'll kill the machine's battery, and a user will be able to deduce that it's your app, and that's probably not going to fare well. In the case of memory, which is also a very critical resource, you don't want to have bloated memory usage or memory leaks or just a general issue with memory allocations, because especially on lower-end devices, you don't know what the policies the memory manager will impart on your app, such that you want to use as little memory as you can so that the likelihood of you being terminated or paged to disk or affect the responsiveness of the rest of the machine is as low as possible, right? So there isn't a magic number there as far as how much memory should you use, but you want to use as little as possible, right? Okay. So essentially, the term you might have heard a few times this week, or maybe you haven't, and if so, that's cool, because I can be the first one to impart you with this magic wisdom. But those four areas, essentially, that I just touched on, kind of fit into this slogan that we have at Microsoft that's fast, fluid, and efficient, right? Those three principles are things that if you try to abide by, you strive for, then you're likely going to have a good success, right? Because you're going to have, by definition, a very well-performing app. And so that's something that we'll talk about a lot, those three. Okay, so let's now go through those four scenarios that I just covered, talk about them a little bit, and then see how the tooling can help you kind of investigate those problems. So the first ones that I mentioned, the resource loading, page loading, and the UI responsiveness, as well as the frame generation, frame rate, keeping up with it, in order to really be able to understand and diagnose those types of scenarios, it's important that you have a basic understanding of the way that the platform actually executes your app, right? You don't have to know the super lowest level. You don't have to know what code. Like, you don't need to be opening up WinDBG and examining the virtual memory of IE. But regardless if you're building a Windows Store app with JavaScript or just a web app that you want to be able to run in IE, it's going to be very beneficial for you before you try to use the tools to diagnose things, to understand the pipeline. So before we get into it, let's just quickly set that stage, right? So the way that a web app works, whether it's a Windows Store app or a website, is fairly simple, right? You have network requests that have to be made. So in the case of a website, the HTML file. So go grab it, right? Once that content comes down, it has to parse that HTML, right? Because the HTML file is just text. That text isn't providing any interactivity. It doesn't provide any UI to the user. It just provides a semantic content describing the content that you want to make up the app, right? And so you have to parse that. Now, many of you are familiar with the notion of the DOM, right? And the DOM is just the consequence of the parsing stage. So after IE, or Trident, the code name you may have heard for the rendering engine in IE, After it has downloaded your resources, parsed the HTML, it outputs from that a DOM tree. And that DOM tree is the live, interactive, fully connected tree graph of elements that make up your content, right? Now, in addition to just HTML, you have CSS that needs to be parsed, and that makes up the style properties of the DOM. You also have JavaScript that needs to be executed, right? And so the Chakra JavaScript engine executes your code as it's parsing through your HTML file, right? Now, once the DOM tree is built up, that provides the structural shape of your app, but that doesn't provide the visual aspects of it, right? And so the next steps is this notion of formatting. And formatting is just the act of saying, this div of ID foo, what CSS properties apply to him? Because, right, the way that essentially HTML works is every element has to have a value for every possible style property, whether it be width, background color, transform, etc. And so in order to do that calculation, the browser has to go examine all the CSS that you've provided to the app and then determine which of those rules match to which element. Once that's done, there's then another step called layout, right? And one thing I forgot to mention, too, is this general pipeline is actually the same for any browser. So I'll mention specifically IE, because we're going to dig into the tools. But really, once you kind of learn this pipeline, it'll benefit you for web development in general, right? But layout, what that does is, imagine when you're writing your CSS, HTML, JavaScript app, and you specify a property like width in a percentage or in an M value, right? And so whenever you have these situations where there is a stylistic property that is dependent on the computation of another element's geometry, then something has to actually lay out the page to figure out, well, when you say width 50%, 50% of what, right? And so it then has to say, okay, well, what's the width of the parent of this element, which is the CSS standard for how percentages are calculated in the case of width, at least. And so that's the process of layout. So it's essentially taking the relative values that formatting came up with for each element and turning them into absolute values. So everything has a width, everything has a position, everything has a value for all of its style properties. Now, out of that comes what we call the visual tree. And this isn't something that you can interact with from code, but it's just useful to know that ultimately what you want to do is get from your code to a visual tree as quickly as possible, because once the platform has that, it can then paint to the screen, right? And so what this is doing is it's going to, under the covers, call a bunch of DirectX APIs in order to translate your DOM and CSS into pixels on the screen, right? And so that's the general pipeline. And the reason that I wanted to highlight this is because when we go into the tools and we start profiling stuff, you're going to realize that having a basic understanding of this pipeline will make it a lot easier for you to understand and diagnose problems. OK. So real quick, 3 things when you're looking at a JavaScript, HTML, CSS app that you want to typically think of is, do I find any work, any CPU utilization that I can eliminate completely, right? And if you can do that, that's the best. If you can eliminate it, can you optimize it? And if you can optimize it, can you defer it, right? Because remember, as I mentioned, you want to get pixels on the screen as fast as possible. You want to have your app respond to the user's interaction as fast as possible. And any work that doesn't contribute to those 2 goals is superfluous and has to either be totally ripped out or pushed off. OK. So now that I just spent a bunch of time talking high in the clouds, let's actually go into the tool and see how we might go about diagnosing some of these types of scenarios. So of course, this went to sleep. OK. So let me come and run this web app that one of my teammates built called Contoso Cocktails. And it's very simple. It is really just a cataloging site that has a bunch of cocktails on it, and when you select one of the cocktails, it gives you what are the ingredients and the recipe for doing it. Now, when we come back to the app, did anybody notice that but me? Right? If I hit refresh, I mean, I have to give Andy, my coworker, credit for making a nice site, but the thing is certainly not the fastest site in the world, right? There's a very perceivable black screen, right? And there's any number of reasons why that could be a problem, right? But traditionally, with the tools that were available to you in F12, people thought of either one or the other type of problem as being the culprit. Was it a network latency problem, right? Maybe there was too much time spent on the server, or maybe there were a bunch of superfluous redirects, or maybe the service that I called to get the data for the cocktails aired out, and I had to do some recovery thing because there was a network tool in IE. And so it was easy to figure those things out. Or you might have thought, oh, maybe it's a JavaScript problem because there was a script profiler in F12 that was easy to use and you could diagnose it. But what if the performance problem actually lied in one of the other steps in that pipeline that I just mentioned that IE uses to execute your app? Formatting, layout, parsing, right? Those were essentially blind spots to the user if you were profiling the performance of an app. But now, in F12, the F12 developer tools in IE11, we've introduced a new profiling tool called the UI responsiveness tool that is essentially a profiler that examines the entire pipeline of execution that I just mentioned while you're running an app. And so this lets you capture a trace of a problematic scenario and then essentially see what's the bottleneck. And that bottleneck could be any number of reasons, and the tool will make sure that whatever it is, you'll be able to know, right? So let's go ahead and start the tool. Let's come back, hit refresh, wait for it to finish, and then let's hit stop. OK. So let's talk about this for a moment. There's a few things going on here other than the fact that it looks awesome. But hopefully that's not the only value of this tool. OK, so let's step through each of the components of this guy one by one. So the top graph is showing you this is the period of time during the trace that your app was utilizing the CPU. OK, good. That's interesting, right? That's going to indicate, OK, that's where my app was running. That's where it was processing input. That's where it was rendering UI. In addition to showing you when it was utilizing CPU, it attempts to break down the CPU utilization into the conceptual subsystem that was running at that point. And those subsystems map to the pipeline that I just mentioned, right? So loading, if we hover over this, this says indicates time spending retrieving app resources, parsing HTML and CSS, right? So all of this blue that I see here, and we'll dig into this more, right? You don't need to memorize this. But from a very high level, I can see that there's a lot of parsing going on throughout that entire period, which seems suspect, right? Because usually, as I mentioned in that pipeline, you expect to parse HTML up front and then execute script and generate the UI. So you don't necessarily expect to see parsing be pervasive throughout the entire run of an app. In addition, scripting, this is going to represent any DOM events, handlers, any timer callbacks, any request animation frames, right? So any essentially script-based entry point into your app that is going to represent user interaction, right? So we see a bit of script, but not as much as some of the other resources. So garbage collection. Garbage collection might be something that seems very arcane and uncontrollable, and it kind of is. But unfortunately, as I mentioned, there are plenty of profiling tools that show you JavaScript execution, show you network, but they might not show you the whole picture. And there's many, many apps where their biggest bottleneck is actually garbage collection, right? And I won't get into it too much, but effectively, because JavaScript has to continue to free memory that you release, if you're having a ton of object churn, where you're creating new objects over and over and over again, that's going to have a performance penalty on your app, right? And so it's important that for you to have that full view of the app's execution, that you actually know, hey, you're doing some work that's requiring the platform to have to keep up with your memory usage. And we'll drill into that more in the next demo of the memory tool. So then styling is the formatting layout. So this is the cost of having to generate your UI. Rendering is painting, and then image decoding, right? Image decoding is another area that many folks might not think about as actually having a cost, right? When you have a JPEG or a GIF or a PNG, that file is essentially like a little zip, right? It's super compressed, and it has to be expanded into a bitmap. And that takes time. The larger the image, the more expensive it'll be, right? OK, so that's what this is doing. The second graph below, though my mouse went crazy there, is the visual throughput. And what this is showing you is when was your app painting to the screen, when were you making visual updates, and during those periods of time, what was the frame rate that it was achieving, right? So essentially, the goal of this graph is you want to look for dips, right? Like you hear 60 FPS as being a magical number that you want to achieve, and that's not always true. Like 24 frames per second is what most movies play at, and people seem to find those to be fluid. But the 60 FPS comes from the fact that many monitors have a refresh rate of 60 hertz. And so mapping to that refresh rate allows you to achieve 60 unique opportunities to present a fresh visual to the screen. And if you want to achieve that, then you probably don't want to have situations where you have these dips, right? So you see here we go from 66 to 21, and we might want to investigate why it was that that dip happened. OK, so let's go ahead and take a look at the app loading scenario. Let's say we want to make sure that this app and all of its resources are downloaded as quickly as possible, and anything that gets in the way of that, we're going to rip out. How would we go about doing that? Well, if you notice on the ruler, there's this little marker here that if I hover over it, it tells me this is the point where DOM content loaded happened, as well as, in this case, because I ran the trace for so long, load happened. So this tells me this is where the resources of my app were fully finished loading. So what I can do is say, OK, great. Let's go ahead and select this period of time up to and including that mark. And I want to understand what happened in that period of time. And is there anything I can eliminate or optimize, right? Because I want this to be as quick as possible. Now, as soon as I make a selection, you notice that the Gantt chart down below updates live, right? And so what the Gantt chart down below is it is the time-based sequence of events that provide a lot more semantics on top of what the CPU graph is showing you. It isn't going to just say script. It's going to say what script. It isn't going to just say styling. It's going to say what elements were being calculated for their layout right now, right? And in a way, once you become familiar with the way the IE pipeline executes apps, you can almost read the Gantt chart as a story. So if we come down here, we can look and see a couple of things. So here's the HTTP request for the main website. And once that was done, speculative downloading occurred, which that's a IE thing that basically says it went ahead and parsed through the HTML to find any URLs that it thought you were going to need in the future, so that by the time you needed them, you already had them downloaded. And that's why you see all these subsequent HTTP requests kicking off. Now, initially, this alone might be a red flag, because there's a lot of subsequent resources being downloaded here. We see jQuery, which is pretty standard. We see handlebars.js, cocktails.js, so that's probably the app-specific JavaScript file. Then we see 4 CSS files, 3 of which seem to have a language-specific prefix. So that's also very suspect. And then we have more other JavaScript libraries that seem to be possibly unnecessary, right? Like maybe the developer who is doing the site optimistically decided to add a whole bunch of libraries to evaluate which ones we were going to use, and they never got removed. So we're starting to see a pattern here that we might be able to follow. So if we traverse down let's start looking and seeing some other things. So after the downloads finish, you notice here is HTML parsing. Remember, that was the next step in the IE pipeline. Once there's content, let's parse it. So if we go and we look and see, okay, two things on the Gantt chart that you'll notice kind of front and center are these two labels next to each event. What that is telling you is the one on the left is the inclusive time. This is how much time it took for this event between the point it started and the point it ended, right? That one's pretty simple. 33 milliseconds. The one in parentheses is called the exclusive time. And so that's saying this is how much time this event specifically spent during that duration. And the reason that that might be anything less than the inclusive time is because an event triggered other work, right? And so the pipeline, even though when I drew it, it looked like this nice linear path, it really can end up being reentrant. And so in this case, as it's parsing HTML, it encountered a script or a script block, and it had to switch gears and go execute that JavaScript. And so in this scenario, the HTML parsing was actually very cheap. What it was is it was evaluating script. So we notice here that it says it's an inline script. So if I select this, and I come over, and I say, man, what is this guy? I can hover, and I see this is actually jQuery. Right? So let me zoom in. See the script URL here. jQuery. OK. So that tells us affirmatively that including jQuery into our app costs 33 milliseconds of load time. OK, that's cool, right? That gives us the opportunity to know whether we have to optimize it out. In this case, we're not, right? Now let's keep going down. So after that script executes, you notice that a layout on the HTML element is performed, right? So this is kind of a step along the initialization process that is not too interesting. But as script executes and your app is beginning to run, it's starting to calculate style information and position of elements as it finds them, right? So it started parsing HTML, it found the HTML element, it had to go execute script, and then as soon as the script finished, it came back and said, OK, great, let me go make sure that I position that element that I found when I did the parsing, right? So then it comes back to do more parsing, and in this case, we see yet another script. And if we select this guy in this case, that is handlebars.js, right? And so forth and so on. So we could read this like this story, or we could say, I just want to know what was the most expensive event that occurred during this period. I want the lowest hanging fruit that I can go ahead and solve. And so if you want to do that, you can go and sort by duration instead of by start time. And now, at the very top, you notice in this case, HTTP requests are near the top because they were very long in duration. But those weren't actually CPU bound, so I'm not too worried about those unless my app was dependent on them. But what I do see is this HTML parsing event that is 246 milliseconds long. And I'm actually super happy that it got there, remember? Because when I showed that quote at the beginning and I was saying 250 milliseconds is the number, give or take, that people can perceive. And so we know for a fact that in the process of loading this page and parsing the HTML content, that there is 250 milliseconds of load time being taken up to process resources, and that could be something that we want to optimize. Now, I already mentioned the notion of exclusive and inclusive, and that events can trigger other events. And so when we see this guy, even though the HTML parsing is 246 milliseconds long, only 26 milliseconds of that was actually parsing HTML, right? So that tells us that the majority of this work was something else. Now, if you want to quickly kind of build the mental model and say, OK, well, what was that something else? You notice peeking out in the bottom of the screen here, this little donut chart. And when you select an event, what it'll show you in the detail pane is this is the roll-up of work that this event synchronously triggered so that you can have a quick understanding of what actually is the cause of the problem. So in this case, if I hover over the 87%, we see that it's script evaluation. So in my HTML content, there is enough script files being statically included that it is causing the majority of execution time for just the general scenario of my app getting up and running, right? So let's go ahead and look at this and see what the breakdown of that is. So we see here, this one's super cheap. Here's one that's 113 milliseconds. This is Ember.js. Here's one, this is MooTools, 51 milliseconds. Here's Knockout.js, 12 milliseconds. And Angular.js. So collectively, there's close to 200 milliseconds of time just executing JavaScript files that we might actually not need. And so in fact, now that we are aimed or armed with this information, let's go back to the app and let's actually just go ahead and optimize those resources out because we don't need them, right? As I mentioned, the ultimate goal of doing any perf analysis is finding superfluous work that you can completely kill because that makes your job even easier. And so in this case, that's what I'm going to do. I'm going to say, these 4 scripts, we don't need them. And in fact, the second rule that I mentioned is if there's something you don't need now and you can defer it till later, then you can do it. So in this case, you notice that there seems to be some style sheet files that might be pulled in dynamically for users of other languages. But until we know that a user is French or speaks Spanish, we shouldn't statically include these files. So let's load that up, or let's make those changes, rerun the app. And let's go ahead and just test to see how much of an improvement we got from that change. There's still clearly other problems. But whenever you're doing perf testing, you really want to be able to measure whether you made an improvement. So let's select that period of time between the start of the app and the DOM content loaded, sort by duration, and notice that now the most expensive instance of HTML parsing is only 60 milliseconds. So we just went down from 250 to 60, right? And that's essentially it. That is the resource loading scenario. Like, if you want to make sure that your app loads as quickly as possible, it just comes down to figuring out the cost of every script and CSS file that you load into your page. And if there's something that isn't necessary, rip it out. So, OK. So now, let's take a look at the other glaring problem with this app. And that is, now that we have the content coming back quickly, it's still taking a long time to render the cocktails to the screen. So let's drill into that. So I'm going to restart, refresh the page, and then I'm going to hit stop. So let's just do this. I'm going to collapse these. So you can collapse those if you want to get some real estate back. And I had duration sorted by default. But in this case, because I haven't made a selection, I'm essentially saying, I know there was something really bad going on in this trace, and I just want to know what is the most expensive individual event during the entire period, not just during a specific time. And so if you don't make a selection and you sort by duration, that's what you'll see. So if you notice here, right up at the top, we see that there was an immediate timer, right? So the app called setImmediate, which then had a callback that actually spent 1.73 seconds. And of that, half of it was JavaScript, right? So we could look over and see, well, what's the rest? Well, there was 29% of HTML parsing, 27% of layout, 24% of executing the timer, right? So that starts to mirror what we saw in the CPU utilization graph. Remember when we saw all the blue, and we thought, man, that's really kind of suspicious that there's all this parsing happening throughout the trace. And so now we know that there's some timer that's firing that is actually taking up way too much time. But what timer is it, right? There could be a lot of timers running in the app. And so you need some way to be able to correlate this script instance with actual code. And so if I come over to the detail pane, you notice that it tells me the name of the callback was add cocktails, and the source location is this. So click this link. And then spin around the screen. But here it is, right? So this function, this function is being called, and it's taking 1.7 seconds to run, right? And we know by looking at the donut chart that a lot of that time is spent doing HTML parsing, but we don't maybe necessarily understand why. So let's go back to the UI responsiveness tool. Let's change the duration or the sort back to start time. Notice it kept my selection, because in this case, we want to start kind of seeing where the flow of execution is occurring in the app. So if you notice, in addition to timers and DOM events and so forth, the tool will also show you every instance of a DOM operation that you made. So in this case, set inner HTML. So this is telling me that set inner HTML was called on the div whose ID was cocktail summary container. And when that was called, what that did was it triggered HTML parsing, as you might expect, right? So the pipeline isn't necessarily linear, because HTML parsing exists at the beginning of the page load when you pull down an HTML file. But if you do an inner HTML call on an element, it only makes sense that it's going to have to parse that content. It's going to have to understand what you gave it, construct it into the DOM, and then be able to present it to the screen. OK, so that makes sense. So this code is setting inner HTML and having to parse. Then it calls offset width on the same div, cocktail summary container, which in turn triggers layout on the body. The body in turn triggers layout on the root container. The root container has to calculate the text within it. The summary container has to calculate its layout. That in turn triggers style calculation, and so forth and so on, right? So you start to see how very simple code can have this cascade effect, where the code here is accessing the offset width potentially unnecessarily of the element. And because the browser, remember I mentioned that certain geometry properties aren't known up front. They have to be calculated, right? Every element, unless you specifically say width is 500 pixels, the browser or the platform has to figure it out. And so if you, in script, say, hey, what's the width of the guy that I just jammed HTML into? You're forcing it to have to go give you the answer to that question immediately, versus being able to wait until it's going to paint to the screen and it can batch things up, right? So this is essentially a very canonical example of an anti-pattern of doing unbatched, synchronous HTML parsing and layout, right? Because if you notice, this just goes on and on. This is what we call a death by 1,000 cuts problem, right? So what the app is doing is it's looping through every cocktail, generating the HTML, and then adding that HTML to the live DOM, which is synchronously forcing it to parse it and then calculate its geometry. When in reality, we could easily generate the HTML for the whole page and add that once, which will batch this whole operation, and it'll be way faster. So let's go ahead and fix that, right? So keep in mind, this is 1.73 seconds. OK, let's go to Visual Studio. Let's go to our scripts file. So remember, when I did the link to source, I was able to see that the function add cocktails was where the problem was. So that gave me the indication to come here. And we see here that there's this data.forEach, so it's looping through all of the cocktail information that it got back from the server. It then calls this add cocktails function, which, lo and behold, look at this. So summary template, or tamplet, it's kind of a weird typo. That's inconsequential to the demo. It's generating HTML using handlebars, remember? And we know that because you saw it in the trace. That's the thing, is with these performance tools, you can't hide any of your behavior from people. It's generating the HTML. It's plus equaling the HTML to the whole container. And then, for some reason, it's setting the width of the container to the offset width. So it's like it's dynamically asking, hey, now that I just added more content to you, give me your width again and make sure you keep growing. But that's potentially a naive solution, and it's just totally unnecessary. So let's go ahead and just do this. Because one thing that's very important is the more that you allow the platform to do the work for you, the better. And so in most cases, you want it to figure out position and sizes for you, right? That's the notion that's great about fluid layouts. Really, you only want to have to give a width or a height if there's no way that the platform could determine how you want it to be on its own. But in this case, There's no reason that I need to be telling it. And so I'm actually forcing it to come up with an answer about width over and over again when it doesn't need to do that. In addition, let's generate the HTML for this whole file all up front and then do a single inner HTML. So instead of having this function generate HTML for every element and then add it to the page individually, let's go ahead and do this. Let's loop through, and let's add the HTML to a variable, and then at the end of all that, let's add it. Right? So it's a very simple change, but effectively we've just batched it. Right? So this is that other principle that I mentioned, that if there's something you can optimize, do it. Right? Like, you've maybe heard all these terms in performance, like spatial locality, where just any time that you can do a single operation that's going to share the same data in memory, that's going to be quicker, right? Because the CPU is going to be able to access registers and shared cache, and it's just going to run super fast. Whenever you have this notion of having to switch between stuff over and over again, HTML parsing, script, layout, parsing, script, layout, that's going to be slow. Pretty much any time, right? Not just the web platform. But a specific example is, do not try to do too many things over and over again. So, as kind of maybe a pro tip, when you're using the UI responsiveness tool, if you see the CPU graph from a very high level looking very interspersed, that's a good chance that's a problem, right? Okay, so let's rerun this guy, and let's see what we got besides an error. From what? Let's see, what did it say there? Unable to set. Okay, well, let's do this. Let's use the new F12 debugger. Go to our cocktails page. Add cocktails. Awesome. Scroll down here and see what might be going wrong. Okay. This is undefined. Okay. So instead of doing this, let's see if we bring up the console. Let's see how we can access this guy. Cocktails. Where's he defined at? Cocktails.summary.root summary. Okay. Cocktails.summary.cocktail. Okay, great. Little live diagnostic. Whoa! I didn't even have enough time to apologize for the bug before the page loaded. That's pretty sweet. Okay, so but don't ever take my word for it. Just because something seems faster doesn't mean it's actually faster, right? Because as I mentioned, there's a lot of devices that are going to be much slower than this super mega powerful laptop that I have right here. And so what we want to do is deterministically know, did we get that instance of the immediate timer down from 1.7 seconds or not? Okay, so let's go ahead and close the console. Let's run this guy, hit refresh, hit stop. I mean, it was perceivably faster, but still. And automatically, this is looking pretty interesting. So in fact, I hadn't mentioned before, you can zoom in on this graph. So if you want to get more granularity, you can. And so let's sort by duration. Actually, let's zoom all the way out. .42 milliseconds, down from 1.7 seconds, right? That's a huge win. And if we look at this now, and say, okay, great, with the change, now how does it look? It looks exactly as you might expect. There is a single call to set inner HTML on the div cocktail summary, which is what we did, and as you might expect, that triggered a single instance of HTML parsing. Now, if we come down here and look at the layout, you notice that it was able to do a single layout for every single cocktail that we added, right? So we just batched up the whole thing. We said, here's one HTML. Bam, go parse it. And then once it said, OK, great, I'm going to wait until I absolutely have to calculate the layout for that content to do it, because that way I can batch it. So it was about to paint to the screen, right? And then it had to go force this. So if we then look after the layout, notice here's the paint. So that's where it actually said, awesome, I have all the content, I have all the CSS properties, now I'm going to go push it to the screen. OK. So that was diagnosing page load and responsiveness, right? So the UI responsiveness tool, there's a lot of data there. With great power comes great responsibility, right? But if you make a point to try to learn and internalize that pipeline that IE is using to execute your app, it can be used to effectively diagnose issues that would have otherwise been very hard to nail down because you weren't seeing the bigger picture, right? The fact that offset width was in turn triggering synchronous layout would have been a total blind spot if you were just using a JavaScript profiler. The fact that making all of those individual calls to inner HTML was causing you a major problem would have been totally opaque to you. Knowing which individual JavaScript files were the ones causing the most load time cost would also be totally opaque, right? And so essentially, this tool is trying to give you that broad view of the world such that you have the opportunity to make informed optimizations. OK, so now let's switch gears quickly and talk about a topic that most people don't like to talk about, and that's memory, right? And memory is very important because people run apps for a very long time. People run websites or apps on low-end hardware that might not have the most memory in the world. And so you want to make sure that if you can streamline your app's memory usage, then you should. That's just a good thing, right? The Windows 8 and Windows 8.1 Memory Manager has policies in place that it will start terminating apps if memory pressure on the machine gets out of control. What the exact policies are non-deterministic, right? But as I mentioned earlier, you want to just put yourself in a position that you're going to be as resilient as possible to memory pressure on a machine, that you are as resilient to being able to have a user switch back and forth to your app and all of its memory still be loaded in RAM because the operating system didn't have to page it out to disk to make room for something else because you were just bloated, right? And so when you care about memory, the three areas that you really end up finding yourself interested in is memory bloat, right? So this is just you're using more memory than you need to, and you can optimize it, and you can be more streamlined with the same functionality. That's just kind of a win, right? It's essentially the exact same principle that I mentioned in the other demo, right? So either, regardless if you're doing CPU analysis or memory analysis, you ultimately want to do the same things. Can you cut any fat? Can you remove something completely? And if you can, that's just a win, right? And then additionally, do you have any leaks? Do you have a scenario that repetitively leaves around objects that aren't actually freed, right? Because over time, that's where the long-term stability becomes an issue, right? It might be a death by 1,000 cuts in a memory perspective this time instead of in the CPU utilization that we saw in the last demo. And then finally, object churn, right? So as I mentioned in the UI responsiveness tool, garbage collection is actually happening, right? That doesn't come for free. Whether you're writing C# or VB on the CLR, whether you're writing JavaScript, you're paying the cost of getting the benefit of not having to manage your memory for you. And that's nice, but you might find that it can be very useful to cut down on constant churn of recreating objects over and over again. A very common strategy for cutting down on memory allocations and GCs is just caching, right? Age-old tale. OK. So just like I did with the UI responsiveness tool, where I wanted to quickly set the stage for how to think about the problem, I want to do the same thing with memory. So JavaScript is a very interesting language in that it has a fairly easy to understand mental model of how the world of memory looks. It's a big giant graph, right? Every time you create an object, a function, an array, an HTML element, that is an object in memory. Now, anytime a property or a variable or an event handler or a closure points at that object, it is one more opportunity to keep that object alive if that reference goes all the way up to the global, right? So in JavaScript, you have the notion of a global object that it will hold on to anything that it can possibly find. So in this case, I have a few examples, right? So you have $sign off of global, so that's jQuery. You have your object, so some custom thing in your app. You have the window. The window, in turn, is referencing the document. The document, in turn, is referencing your HTML element, which is, in turn, referencing the body, which is, in turn, referencing the div, and so forth and so on. So if you want to remove your object from memory, the way you do that is you have to kill that reference between the global and it, right? Because that is the connection that is telling the JavaScript garbage collection process not to kill it, because you're saying this guy is still wanted. But if you remove that property or variable or whatever it is, and the next time the garbage collection runs, you notice that your object is floating off in space. And so that lack of a reference back to any globally rooted object is the deterministic notion that the GC uses to say, great, he's dead, right? And so essentially, whenever you're doing memory analysis in JavaScript, what you want to do is say, what object do I want to either completely remove or optimize? And then you have to figure out, well, what references are holding him alive that I need to kill, right? And once I kill them, then the GC will take care of it for me, right? When you do foo equals null in JavaScript, you're not actually killing the memory that representative of the object, right? You're nulling out the reference between two objects that later on the garbage collector will see that lack of a connection and it'll remove it. Okay, one other quick concept that I want to talk about is the notion of retained size, because this is something that we'll see in the tool. And every object has its own size, right? A string has a size, a number has a size, a Boolean has a size, and then an object is essentially an amalgamation of those primitives. But in addition, an object can also have what's called a retained size. And what that means is kind of a fancy term for this is the amount of memory that if this object was to be collected, he would take all of this memory with him, right? Because he's the one who's holding on to a bunch of other stuff exclusively. And so in this case, you notice the HTML element is the only guy who's rooted back to global that is holding on to the head, the body, and all those other things. So he's responsible for the whole shebang. But if the window.location object adds a reference to the head, then the HTML object is no longer retaining the head. Because if you removed HTML, the HTML element, the head would still be kept around, because there's some reference that's making sure that it's alive, right? And so you'll see in the tools I'm about to show this notion of retained size, and you're really looking for who's the biggest object that if I get rid of, he'll give me the most bang for my buck. Okay, so let's go back to my demo machine. And in the previous demo, I used F12, and this time I'm going to use VS, because the exact same performance tools exist in both environments. So whether you want to do light iterative development and diagnostics in the browser for a website or a web app, or you want to do development for a Windows Store app using JavaScript, you can take advantage of the exact same tools. So in this case, let's go ahead and close all this. And in Visual Studio, there is a thing called the Performance and Diagnostics Hub. So you notice that I went to Analyze. Get out of my way. Analyze. Performance and Diagnostics. And when you click that, you get this really nice landing page that basically says, these are all of the available profiling tools that you can use to determine the performance of this app. And so in this case, I'm going to select JavaScript memory. So I'm going to hit Start. And what that's going to do is it's going to launch the app. And what this app is the fancier, nicer, modern-looking version of that really ugly cocktail site that my coworker Andy built. And essentially, it does the same thing, but in a lot nicer way, right? So I can sit here and scroll through images, see the ingredients, and so forth and so on. Now, I want to quickly show essentially the scenario of solving memory bloat. So run this app, and you want to ask yourself the question of, how much memory is this application using, and is there any opportunities for me to trim it up? And so what you can do is if you come back, you notice that when I started running the memory tool, it's showing me a graph of the high-level amount of memory that the entire process is taking up. That includes not just JavaScript, but if you're having a hybrid app, that would include any managed or native memory. But if you want to understand deterministically what the size of the JavaScript and DOM memory you're using, and then investigate it, that's when you want to take a heap snapshot. So if you come down here and click this, what it's doing is it's reaching into the browser and saying, give me the information of every object you know about and all of their sizes, right? And so when it comes back, you notice that we see a few things. We see here's the size of the entire amount of JavaScript and DOM memory, 31.96 megabytes. Seems fair, but we're not sure why that is that large. In addition, it tells us how many objects there are, 4,330, right? So in the memory bloat scenario, essentially what you're just curious of is, how big is my memory, and is there anything that's egregious in there that I can trim that would help me streamline my app a bit? So let's go ahead and click on this link. And when we click on that, it pivots us into this detail view that is showing you every object that exists in your app at this point in time. In addition, it shows you the identifiers that are used to recognize what that object is, as well as the type. So here's the global, right? Here's an element. This is an object that is referenced as a div whose ID is content host in the DOM. But notice the comma. It's also referenced in JavaScript via a property called underbar element, right? And you'll notice that there's a whole bunch of really nice conventions for helping you understand what an object is. So if it's an HTML element, we'll show you the class and ID. If it's an image or audio or video tag, we'll show you the source. And then the type name also helps kind of give you additional information, right? So if the object was created by a constructor, the type name will be the name of the constructor. So HTML div element. But you notice this guy here, he's got this syntax where it's showing essentially the properties that this guy has because it's an object literal. So you created this object, and he's not really of a type, but the type of him is this set of unique properties. OK. So finally, on the right, you see retained size. So that's that number that I talked about before that's saying this is how much memory that this guy is owning that you could totally get rid of if you trashed it. So let's investigate this a bit. So we saw global is got 31.96 megs. OK, so let's expand him, and that's going to show us everything he's referencing. We want to know, well, what is the biggest that he's referencing? So we see that he's referencing div ID content host. That's 29 megs of that. What is he referencing? That's referencing div class win disposable page control. In turn, that's referencing a div. In turn, that's referencing another div, which is referencing a win control object, which is referencing a div, which is referencing another div. And finally, we get to the bottom of what's the actual source of the majority of our memory. See this? Image class, item image, source martinis.jpg. And if we scroll over, there's a single image that is taking up 25 megs of that 31, right? So that is a pretty obvious example of memory bloat, right? Like the entirety of this application is 31 megs of JavaScript and DOM, and a major percentage of that is this specific image. And so what that tells us is that we probably have this image loaded in a size that is high definition, even though we're only showing it in a tiny little thumbnail in the little viewer. And so that's causing us to have a bloat of memory that actually adds no value whatsoever to the user, because they're not able to zoom in and see it any richer, right? And so with this, it gives us the opportunity to make an informed decision around what is the size of our memory and what is the largest object that I can in turn free up. Okay. So that was kind of a quick overview of memory. There's a lot more to that tool, but ultimately memory analysis comes down to just traversing down objects like I showed you and finding who's the biggest and then figuring out how to get rid of them. Okay. So in summary, we just kind of went over a lot of content very quickly. I wanted this to serve as just a foundation for you guys to understand that memory, UI, responsiveness, performance is important. It can have major impacts and effects and benefits to your application, and it can be fun-ish if you end up liking the tools, right? So in addition, whether you're using Visual Studio 2013 or F12, we have the tools that are going to help you to be able to solve those problems for you. And so finally, try out the tools, send us feedback. We want to hear from you guys more. We would love to get emails. Please come up and talk with me after this. And thank you so much for coming. I hope you guys have a good trip back home.